Welcome back, everyone. As promised, I have Fei and Barry here. We're going to talk a little bit about high-performance computing, HPC. But before we do that, I think everybody knows who I am by now. I'm Art Baudo, and I'm in the product marketing area at Amazon. But let's have Fei and Barry introduce themselves. Fei?
Hey, nice to talk here. My name is Fei. I'm leading the HPC solution organization. We develop solutions and architect solutions for the HPC customer on AWS.
Welcome.
And I'm Barry Bolding. I lead worldwide advanced computing, which means I lead teams that engage customers around areas like high-performance computing, quantum computing, autonomous systems, and digital twins.
So Barry deals with a lot of really big words, I think, is what I just learned for his title. So, but let's first talk. I introduced with Martin here a little bit about HPC, but I think for everybody who's not familiar with HPC, maybe we could provide a brief overview of HPC and how it's used in industries and science domains. Yep. Barry?
I got into high-performance computing several decades ago, and as a scientist, I was working on problems that were so complex they couldn't be solved in experiments. And so simulation and modeling was the key to solving those problems. And what I've seen over the last few decades is that innovation in silicon has changed the way that we solve problems. We now solve these problems, whether it's an engineering and design problem, or whether it is a scientific discipline trying to solve a basic research problem. We solve these problems in many times using simulation and modeling. So high-performance computing is the methodology used to solve these problems. Modeling and simulation are what the researcher or engineer is doing. Some examples of that can maybe make it a little clearer. Yeah. So, for instance, if you're designing a car, people don't think about it, but you need simulation and modeling for almost every part of that car. You need to simulate the combustion in the engine. You may need to simulate the vibration and harmonics inside the cab to make sure it's a quiet ride.
The airflow over the vehicle.
The airflow over the vehicle.
Any of us who put a bicycle rack or something on the car know what the impact is.
Exactly.
Right, an engineer has obviously tried to really engineer stuff, right, to give you the best.
That's exactly right.
Mileage.
And the cool thing is, because of the silicon innovations and the networking innovations that we've made over the last few decades, we've made it possible to actually simulate the whole car as an entity it's a complete entity, using all those components at once. So that's just one example. And then that migrates down to simulating your cell phone and dropping it, drop testing on tablets and cell phones, or drug discovery, looking at innovating and developing drugs more quickly. As Martin mentioned, many people don't know, but AWS was used by many of the drug discovery companies as they were trying to solve for vaccination. But Moderna was looking for faster ways to innovate and solve for vaccines for COVID, for instance.
And I think another thing is that earlier discussed from Nafa and Gary were how we also at AWS simulate using our own silicon here in the cloud, how to test the very silicon that we work off of. And as somebody that worked once upon a time in the phone space, even your example of dropping the phone, I mean, in the past you were breaking equipment, then there's a cost to all of that, right? So some of the simulation is also, to be more efficient in how you operate as well.
Another example, ARM, one of our partners who helps us, in the development develop the architecture for Graviton, actually runs over 50 million simulations a week on AWS in order to help with their design processes.
50 million. The numbers we always talk about are a big surprise, right? I mean, the two of you deal daily with large numbers here. But so one of the things that we were talking about is where is HPC today, and what are some of the primary technologies that derive the development and success phase of high-performance computing?
Yeah, so if I look at this area, is there's three key pillars that enable those very, very large-scale simulations and computations. And the first pillar is really the chip design, the cloud service we are enable as the infrastructural backbone of those simulations. And of course, today we have talked a lot about those silicon new innovations, so we'll be in that pocket. And the second part is actually the algorithm itself is is essentially how you take a problem, think about mathematically and logically, how you can design a solution by using those silicons or hardware and such. And also recently I've also started seeing that algorithm can be also smart by taking advantage of the latest development, for example, AI and machine learning. That can also think about is acceleration of our simulation.
Yeah.
And the last pillar of this is really thinking about, you're not just thinking about solving one problem, right? You want to solve this at a really large scale. That means you want to, your algorithm take advantage not just one component of the compute, but many, many of them. So we need to think about the maximum scale of parallelism that every single individual of those compute device can compute, and they can talk with each other, they can communicate very efficiently with each other. And that is the last pillar of this technology, is that parallelism.
Yeah, and you also used a word there, Fei, the efficiency of being able to communicate back and forth. I think we've used that in a lot of different areas, but a lot of this is about more efficiently doing a process or a task to provide better information. So why is it, do you think, Fei, important for HPC customers to be aware of and invested in those latest silicon innovations?
Yeah, I think there are several factors driving those. Number one is what we call Moore's law is really slowing. And for the audience who may not be familiar with this terminology, I think in layman's language, it's really talking about an observation how the compute power can accelerate during the time, right? So usually we talk about the computing power on a single microchip can double every 18 months. But that trend has been slowing down, which means that for a customer, you have been really being conscious about choosing the best and performance chips for your computation workload. Right. And the second part is really driven by the large volume of the data, the complexity of those HPC work become more and more increasing complex. And also, people are looking for more and more accurate of the simulation result.
That's right.
All the three basically means that your workload become larger and larger, right? And we I think today talk a lot about machine learning, deep learning. That's just one example. Back in 2017, the deep learning model is at a scale of 100 million parameters. And today, the latest model is at the scale of 500 billion. So that's like 1,000 increase of size in just 6 years. And that's just one example of that.
Huge,
it's
right?
huge.
I mean, these increases in the last several years alone, you know, the amount of data that people are processing, Fei, is tremendous here, right?
Exactly.
It's just great.
Yeah, exactly. And lastly, I think that's also, we talk about on a single chip that computing power has been constrained, right? So you have to think about with the diversity of the workload compute, we need to think about design chips for every single different type of computation. And we have been seeing, right, that there's a lot of growing in the space in terms, if you go to an auto-driving car, there's special chips in the car for the inference in the car, right? And today we also talk about a lot of AI chips in inference, in training. If you think about this, it's just also different type of chips designed for different type of computation in different environment. What this means for the customer is also they need to think about what is the best choice for them, right?
Right.
Yeah.
And I think the other thing we've talked quite a bit about is you know, choice for customers and delivering the best, delivering, you know, lots of offerings, but that allow customers to establish, you know, the right boundaries and make good selections for what they're able to do. And that's kind of what we're talking about here. So maybe we could talk about some examples about how HPC customers have been able to drive benefits from the silicon innovations that we've introduced. Barry?
Yeah, this is the most exciting because at the end of the day, we want to see customers creating results, and those results changing our world for the better.
Yeah.
So if you take a customer, whether it's a company like Aurora that wants to build an autonomous truck, they may want to ingest huge amounts of data, volumes of data, and then they want to do training, machine learning training on that, to train a model that will help the truck make decisions. Yeah. But before you send that model back to the truck, you need to do simulations on that because you want to test all the edge cases. So they want to run millions and millions of miles of simulations on that model. so with that complex workload, that complex workflow, they have to then think about, okay, how can I optimize several things? I need to optimize the price performance of the application that's running all of this. So price, performance, cost. And so having innovative silicon lets them fit the right piece of that application onto the right innovative silicon, whether that's our newly launched HPC 7G instances, which are purpose-built for high-performance computing simulation for that piece of the workload, whether that's our inferentia and trainium technologies for the training of the model portion of the workflow. They can fit the best part of the application to the best silicon to get the best price performance. Now, then there's the energy efficiency, because in our world today, many companies, they really want to show the benefits that they are putting Earth first in the way that they're doing simulation. And so they care about the amount of energy used per simulation that they're doing. And that's where, if you make the right fit, you're actually maximizing that. And here at AWS, with our innovative silicon, we've done that. We've really taken into consideration how to have the most energy efficient. And then also some companies are actually solving problems that relate directly to energy efficiency. For instance, we have customers like DTN who are doing localized weather forecasting so that they can help farmers make decisions about when to plant on a particular field, on a particular acre of land. And you need that localized weather model, and you need that simulation. It's really important to have the right technologies underneath and then to produce the right results.
I think that, by the way, is a great example, because I think a lot of times people out there probably don't. It's a great example of a workload, the farming stuff that, people just think, oh, we throw down some seeds or a seedling and some crops germinate, and then, suddenly all of us have food at the grocery store over the weekend. But it's a lot more, it's become more complicated than that, because you're trying to get, it's a business, and it's also trying to get the most yield out of the land that you have and the property, and there's a lot of, and the weather is, you can't make it rain, but you need to know when precisely it may happen.
Well, and another weather application, another farming application, it uses machine learning and simulation and modeling, is that today they're building tractors that actually can, as the tractor is driving across the field, recognize the weed and spot spray the particular weed. Rather than blanket spraying a whole field, you can just apply just the right amount of fertilizer or pesticide to that particular plant. And that really is better for our environment than this broad, pervasive spraying that has happened in the past.
It's more efficient as
more
well,
efficient.
right?
Yeah.
I mean, I imagine now you have less cost that you're spending as well. I mean, that's where the farmer is like, hey, we didn't have to spray indiscriminately an entire field to do that. So
and then the last benefit, and this is really important in high performance computing, is that when you have to solve a problem very quickly, that where time is the most critical aspect, you need to be able to scale your simulation with the parallelism that Fei mentioned. And to do that, you often need, and AWS, our customers often use our Nitro cards that we've designed, and then we've enabled what we call our EFA, or Elastic Fabric Adapter Network, to run on that hardware, and it scales single applications up to tens or even hundreds of thousands of cores. And that parallelism is really critical for solving that time-sensitive problem.
I mean, connecting both the example, the parallelism that Fei was talking about earlier, along with the example here, I think this is a great usage of those HPC models. I think it kind of better helps for, hopefully, at least for me, hopefully for everybody out there, it helps a little bit better explain, some of how HPC is used, and also how it's a part of effectively our daily, and impacting our daily lives as well. So maybe the next thing we could talk about are some of the emerging trends in silicon innovations, and that we could expect to see in the near future from some of those HPC customers, Fei.
Yeah, sure. This area I got really excited about. I think at least I see two trends here. Number one is really the quantum computing in HPC. I think quantum computing, the way I think about it is just yet another accelerator for our computation, HPC computation. But the way that it works, that we need to think about how you can design your algorithm to better use of the hardware itself. And recently we have to work with customer in that area, a customer called Good Chemistry. So they are using the quantum chemistry simulation to understanding a very key component called PFAS. So PFAS, for audience who don't know, is actually one component, chemical component is really hard or impossible to decompose biologically in the natural environment. So it become a very leading concern for our environment and leading to a lot of pollutions. So Good Chemistry is customer, they have worked with AWS to design algorithm that using quantum simulations to understand the component or how can you break this PFAS component so that we allow to develop more economical way to decompose it. So this is one good example, and I feel
I love the example.
It's a social good example, right?
Yeah, social good, and it's also like I think a little bit of it is a health good too. I mean, we are consuming water that has these products that haven't precisely decomposed in them too. So there's like a dual for the environment out there, which totally support that too, but also for the health who wants to be consuming these chemicals too. So yeah, what a great example.
I think that's one example that allow us to think about those really, really large-scale simulations that we probably even today it's a bit hard to do on the traditional HPC, but if we think in a revolutionary way on the quantum, maybe there's a way towards it. Yeah,
I love the example because it goes to show, you know, how until we have been able to look at things from and be able to look at these large data sets, it's been almost impossible to try to tackle some of these problems that are out there. You know, this is Good Chemistry is a great example of, you know, the fact that, you know, we're getting toward being able to have the resources to be able to make the complex calculations that are necessary to potentially get scientific breakthroughs like that. It's a great example.
Exactly. Another area I think that gets me excited is about the generative AI. We have been talking about all day about this. But in that area, I think, which means that we need to look at those specialized AI chips like the AWS training and inferential. For example, we are working with Johnson & Johnson in this area. So Johnson & Johnson, you know, they have a lot of R&D using their machine learning and deep learning everywhere in their R&D steps. This covers their drug discovery, their molecule research, and also to the finally clinical trial step. In every single of those steps, they use deep learning. And we are right now exploring using training and inferential together with them to lower their operational cost in training those models and serving those models in production. And again, we also talk about sustainability. Just Barry mentioned about that. This is also very key to many enterprises because they run those large workload. It's critical for them to make sure they're being sustainable, energy efficient.
Absolutely, and I think your Johnson & Johnson example is great because for those who were here a little bit earlier, we also had a short video from one of the folks at Johnson & Johnson from one of the Jensen is one of their subsidiaries, and you know, they talked exactly about starting that process using inferential and trainium with that. So I think it's a very timely example for today.
Exactly.
And, you know, encourage you to take a look here as well. So. Earlier, we had mentioned that you had mentioned, Fei, that there are 3 core technology pillars that underlie those HPC workloads. So, and apart from silicon, cloud product innovations, what are some other technology trends that we see contributing to innovation in the HPC space?
Yeah, I think we just not talk about the silicon innovation that can help us to think about how we can change HPC. The other aspect, this really goes into the algorithm part of this, is to think about how the machine learning can help with HPC, right? So if we think about the revolution step we have go through, we start from the actually physical experiment, like dropping the tablet on the floor, right? To doing the simulation that you don't have to physically do that. But simulation itself still, if you want to do this at a very large scale, still very time consuming and resource consuming.
Absolutely.
So the idea is to using machine learning and AI to approximate the simulation result so that for human, they don't have to run every single simulation. They only look at the most interesting and promising way, right? So I'll give you two examples in that area. Number one is, I think we talk about the car making, there's all this fluid dynamic simulations.
Absolutely.
And this is, well, if you want to design a car, you want to simulate how the wind will go through the car that can impact the next one following it, right? And traditionally running that simulation is very, very time consuming. And we have developed a machine learning algorithm that can approximate that simulation result. So for human, you only look at a very limited number of design choices and only run simulation on those ones. This dramatically can help you to reduce that simulation result. Another example I like to mention is in the biology domain. So we have been working with Columbia University to develop this deep learning algorithm called OpenFold, which basically giving a biology sequence can help you predict the function of this biology sequence. And the function is very critical because you will know what type of drug you can design for that, what type of function of the protein will tell, right? So it's very powerful algorithm. And again, traditionally, you have to do the lab experiment to actually understand the function of those sequence. Yeah. And now you can use machine learning just like within very fast, you can predict millions of sequence functions.
Yeah, so very.
Yeah, and in both of those examples, we've seen customers speeding up their innovation by over 1,000 because they can explore a wider space of possibilities, and then hone in and do the really accurate simulation or even experiment on just the ones that are most targeted.
I think that's just really key for so many of this, because there's so much information, and you can test every single simulation ad nauseum, but that takes, as we mentioned, a lot of time, and it's not just time, it's also time and effort and money and resources that have to be spent on it. But with this, you're able to do that simulation, narrow it down to the kind of salient few, and then that's where folks like yourselves and others who are experts can focus in on where their resources are best used to say, this is where you potentially have to focus.
And I see this goes beyond to resource saving. This also allows you to innovate faster than before, because you can exploit more design choices than before.
Yeah. That's, and time, I grew up in a house that, the saying "time is money." It was, banged home. But it is in this instance, the time is length of time it is reduced. It allows places like Columbia or someone doing the simulations for the auto to come out with the product even faster. And I think sometimes everybody who has driven in a car, and in the case I normally live in the Bay Area, and we see driverless cars and stuff going around, but when you think about the process just of the driving of the car, but the automobile has so many other simulations, which is why I introduced the conversation about the wind and the resistance, because that's how gas mileage is saved in the vehicle, or and vehicles are exposed to a lot of different elements and things like that. I mean, I don't know about where other people live, but sometimes there's a pothole in the road and things like that, and you have to simulate maybe how to avoid it or what to happen here. So so I think if individuals or companies out there want to prepare themselves to take full advantage of the innovations in this space, what would you recommend, Barry?
Yeah. Well, the obvious one, of course, is to use AWS. But I do think what often gets forgotten in the conversation, especially on Silicon Innovation Day, is software. And it's really important we heard from Hugging Face about the Neuron SDK and the innovations. But in the same way in HPC, we really need the partnerships with our community on software. Today, just to give you a couple of quick examples, we're partnering with Riken in Japan, where they have one of the largest supercomputers ever built. Fugaku is the name of it. And we've worked with them to create a virtual Fugaku on AWS using our Graviton 3 processors. So, and that takes software. It's really about software. And then another example is we're working with Meta and the PyTorch community to optimize PyTorch for these large training algorithms and make it tuned to the devices underneath that. So those are two good examples of how we're using software.
I think they're great examples, not good ones, Barry,
Yeah.
I want to say. So we've put in some information and links for folks to take a look at some of the latest HPC stuff. I do want to just go back and re-mention that, just yesterday we did launch our latest HPC instance, the HPC 7G.
Right.
So take a look at that information online.